Hi everybody. Today I am going to discuss about conditional probability and Bayes theorem. Let's move ahead. Conditional probability, it is a measure of the probability of an event occurring given that another event has occurred. And the Bayes theorem, it describes the probability of an event based on the prior knowledge of the conditions that might be related to the event. Simple way, I can say it is the application of the conditional probability. The conditional probability of A given B is denoted by symbol probability of A given B. This is the symbol. Again, the reverse conditional probability of B given A is denoted by the symbol this, and we can say probability of B given A. Let's move next slide to have more understanding of Bayes theorem and conditional probabilities. Here there is two events A and B. Some portion from both overlapping. I put yellow color. We can call this portion as intersection of A and B. That's what I have written here. A intersection B. Left hand side, we have Bayes theorem. It is for two outcomes. If A and B are two events in a sample space S, this is S, then the conditional probability of A, this one, given B, this, is defined as probability of A given B equal to probability of intersection of A and B, I mean this part, divided by probability of B, this B, having probability of B greater than 0. Now, there is intuition behind this formula. When we know that B has occurred, so every outcome that is outside of B should be discarded. These very important points. So our sample space, before it was S, now it is reduced to the set B. So the only way that A can happen is when outcome belongs to set A intersection B. This is the only case. So to find conditional probability of A given B, we simply divide probability of A intersection B, we can see it here, divided by probability of B. Probability of A intersection B divided by probability of B. Then we get this probability of A given B. Here also there is two event A and B. And some portion from both overlapping. So same way we call this portion as the intersection of A and B. Here also we can see Bayes theorem for two outcomes. But it is with reverse conditional probabilities. Reverse conditional probabilities. Because it says A and B are two events in a sample space S, then conditional probability of B given A. Previous slide we have seen probability of A given B, but here it is B given A is defined as probability of B given A equal to probability of intersection A intersection of B, probability of A intersection B divided by probability of A having probability of A greater than 0. Now for this formula, same intuition like the previous slide behind the formula. What is that? As we know, A has occurred. So every outcome as it is occurred, every outcome that is outside A should be discarded. So our sample space before it was S, now it is reduced to set A. Now only way that B can happen is when outcome belongs to the set A intersection B. I am repeating the things again. B can happen when outcome belongs to set A and B. So, to find conditional probability of B given A, it is reverse. To find conditional probability of B given A, we simply divide the same way probability of A intersection B divided by probability of A, this one. concept is same, but it is reverse. Now we can see two equations. This we have seen in previous slide, this one. This is reverse of this. Now rearranging this denominator, easily probability of A intersection B, it is for both. So we can write equal to probability of A multiplied by probability of B given A equal to probability of B multiplied by probability of A given B. So from these two portion, easily we can write probability of A given B. So this part will be at the top and this will come as a denominator. This is an equation of Bayes theorem also. Now our thinking to see details of this Bayes theorem for n outcomes. Before we did for 2 outcomes, now it is for n outcomes. So this is a sample space S. I put the name S, and this full area is the sample, that is S. I divide total space into 4 parts representing A1, A2, A3 and A4 events. So A1, A2, A3, A4 events. It is a set of mutually exclusive events and as well collectively exhaustive events. So what is mutually exclusive event? It is actually can't happen at the same time. Because mutually exclusive events can't happen at the same time. Like turning left and turning right are mutually exclusive. It will not happen at the same time. And the event A1, A2, A3, A4 also said to be collectively exhaustive if at least one of them must occur. These are the conditions. So here I have written A1, A2, A3, A4 be a set of mutually exclusive events that together form the sample space S. Now here on the same diagram you can see a yellow circle. This is another event that occurs, it is B. Another event occurs, that is B. Now this B has some common area with A1, A2, A3, A4. You can see here. And I put the name for these four portions as A1 intersection B, A2 intersection B, A3 intersection B, and A4 intersection B. So there is four intersections. Now in next slide we'll see the how to make equations for probability of B, because we can see here there are four portions, four intersections. Same diagram. I want to write the equation of probability B. So how to write it? I will add the probability of these four portions. So it looks like that. Because probability of B, it will be equal to probability of A1 intersect with B plus probability of A2 intersect B, probability of A3 intersection of B, probability of A4 intersection B. Now we want to elaborate, we want to extend these equations. So we will use this because probability of A intersection B equal to probability of A multiplied by probability of B given A. Because here we can see probability of A1 intersection of B. So this part we can write it as this. So all this part we will convert like this one. Probability of A, probability of B given A. Because we got this from these two equations in the previous slide. So I am writing in this form. Look at probability of A. I wrote here probability of A1. Probability of B given A. I wrote here probability of B given A1. Same way I have to write. So my equation, now this one. So probability of B equal to probability of A1 multiplied by probability of B given A1. Now we can write this equation probability of B in a generalized form. How it is? Next slide you will see that. this one. So previous slide it was A1, A2, A3, A4. So in generalized form I wrote I equal to 1 to n, because before it was only 4, A1, A2, A3, A4. In generalized form I am writing I equal to 1 to n summation of same formula, probability of B given AI. If I put value of I1, value of I1, so previous slide equation first term will come, probability of B A1, probability of A1. So in generalized form I equal to 1 to n summation of, we can write this equation. In the next slide we will use this to get generalized form of Bayes theorem. And also I brought this equation to show how it comes, because look at this one, A1 means AI, A1 here AI, it means if I put 1 it will come this, if I put here 2 it will come this, if I put I equal to 3 this term will come, if I put I equal to 4 this term will come. In generalized form it is like this. Here, as we know the fact that probability of AK intersection of B, because we want to get the Bayes theorem in generalized form. So we know that probability of AK intersections of B, in the previous slide we got like this, probability of AK, probability of B given AK. Previous slide, our generalized form, we had this term also, but it was with 1. Now here I put K. So we can express Bayes theorem as this. Because probability of AK given B, we can write at the top, I mean numerator, it is intersection of probability divided by probability B. Bayes theorem for two outcomes, we have seen that. Same procedure, formula comes like that way. So probability of AK intersection of B divided by probability of B. Because here given B, so in the denominator it will be probability of B. Now this probability of AK intersection B, already we wrote here, probability of AK intersection B, it will be probability of AK, probability of B given AK. Exactly same thing to be written. Probability of B given AK is written like that, and probability of AK, just I followed this. I replaced this one, this part with this one. And in the denominator already probability of B. But in previous slide we have the generalized form of probability of B. We have generalized form. I can bring it here. This one. In previous slide we had this. Probability of B equal to summation of I equal to 1 to n. We had this formula. So in place of probability of B, I will write this. Let's see. Top as it is in the denominator. I wrote this. See, look at. So this is the generalized form of Bayes theorem for n outcomes. So we can tell this formula, I mean this probability of AK given B equal to this. Bayes theorem for n outcomes. That's all for today. Thanks for watching.